Hello everyone, welcome to the session 6 of module 2. Till now we have covered first come first serve, SGF, SRTF and priority scheduling. Now in this session we shall cover remaining 3 scheduling algorithms. This round robin scheduling, which is designed especially for time sharing systems, and this scheduling it is similar to that of your first come first serve scheduling, but here one additional condition is that it is of preemption. And you should remember one important term with respect to round robin, that is called as time quantum or time slice. What it is a smallest or small unit of time. See, this time quantum can be which ranges from 10 to 100 millisecond in length, that is in general way. Okay, and the next one is the ready queue. Here it is treated as circular queue. So these are the important terms that you should understand carefully, where this CPU scheduler goes around the ready queue, allocates the CPU to each and every process for a particular time interval up to one time quantum. So this is the general time quantum which is given as 1. But in reality, the time quantum will be ranges from 10 to 100 millisecond in length, and it also be specified by the user also. So how do we actually implement the round robin scheduling and also the FIFO queues of process? Here you know that ready queue is of first in first out queue, where assume there are some process they are waiting for execution. Assume P1 has arrived. So once the P1 has arrived, if the CPU is available, the process P1 is taken from the ready queue and it is given for execution. How many times or how much time will be spent by the process in the CPU? It is mainly depend upon the time quantum that what has been specified. Assume here the time quantum is 1 millisecond. So as soon as the process P1 completes its execution, the process P1 is taken from the CPU and it is pushed to the ready queue. So during the execution of process P1, there may be some other process might have arrived and they are staying in the ready queue. Here let's consider example like a process P2 and P3 might have arrived during the execution of P1. So once the P1 has completed, that is a timer has been set to interrupt after the time quantum expires. So the time quantum is 1 millisecond. Once the 1 millisecond is done, what actually happened? The interrupt has occurred and the process has been taken from the CPU and it is pushed to the tail of the ready queue, that is P1 has been placed here. Now which process is waiting for the execution? Now the P2. Again the P2 is taken from the ready queue and it is given for CPU to execute for 1 millisecond. So once this is done, after 1 millisecond, again the P2 has sent to the ready queue and P3 will be given chance to execute. So this keeps on repeating until all the process completes their burst time. So this is how the actually round robin scheduling works. Here the two things will happen, that is when you have a process which with the burst time that is of less than 1 time quantum at that time, so the process itself will release the CPU voluntarily, need not to wait for interrupt to occur. This is one thing. Second is, if the CPU burst which is currently running the process which is longer than 1 time quantum, the timer will go off and will cause an interrupt to the operating system, and then that process will be put at the tail of the ready queue. See, the performance of this algorithm mainly depends on the size of the time quantum. That is, if the time quantum is very large, then this round robin scheduling will act, or it is similar to that of first come first serve scheduling. This is one thing. If the time quantum is very less, then this round robin appears to the user as though each of n process has its own processor running at 1 by n the speed of the real process. See, with respect to the software, we need to consider the effect of context switching on the performance of the round robin scheduling. So what actually the context switching means? It is a process of storing the state of a process so that it can be restored and resume execution at the later stage. And also, it is, in simple term, we can call it as loading and unloading the process from the running state to the ready state. So when you have the larger time quantum for a specific process time, then we need less time that is spent on context switching. But whereas when the smaller time quantum is given, then more overhead is added only for the purpose of the context switching. So you can see this in this diagram. The process time is 10 and the time quantum has been given as 12, 6 and 1, and respective context switching is also given here, 0 and 1 and 9. So assume that if the process is of a time burst time which is given as 10, if the time quantum is 12, then there is no need of context switching. So without doing any context switching, it is executed. So the context switching is 0 here. Assume that if the time quantum is 6, 1 context switching is required. So this is one thing. And if the time quantum is 9, if the time quantum is 1, we need 9 context switching. So it shows that clearly, it shows that how a smaller time quantum increases the context switching, and also it affects on the performance of the scheduling algorithm. And also this graph tells that here it varies with respect to the average turnaround time based upon the time quantum for this respective process for processor. So this is with respect to the round robin scheduling. We shall see with the examples how we can solve using this scheduling algorithm. So let's consider a simple example over here. What is the example here? That is, all the process has arrived at time 0 with the length of CPU burst time which is given in milliseconds, and you need to use the time quantum as 4 milliseconds. So there are 3 processes and the arrival time is given very clearly, it is at 0. So your process, or you can show the Gantt chart here, you can write it like this. The first process is taken, that is P1. As you know that it is means all the processes are in the ready queue. They are waiting for their turn. So P1 is picked first and it is executed for 4 milliseconds because it is greater than, that is burst time which is greater than your time quantum. So it is executed for 4 milliseconds and this is 4 here. After that, the turn will be given to P2 and it has to execute up to 4 milliseconds based upon the time quantum. But here the burst time is given only 3 milliseconds. So I execute only for 3 milliseconds, that is 7 here. And the next one is P3 and I execute for 3 milliseconds, it is 10 here. Now all the process has executed, still the process P1 wants to execute, still 20 minus 24 minus 4, it is 20 milliseconds. Still it has to execute for 20 milliseconds. So the process P1 will start executing now. P1 will execute again for 4 milliseconds, that is 14 here. Again P1 execute for 4 milliseconds, that is 18. Similarly for 4, 22, 26, and remaining is 30. So P1. So this is how it will execute with respect to this process. So I hope this is understood. Let's consider another example where the arrival time has been given and the arrival time are different. In the previous example where we have seen all the process has arrived at 0th time. Now you can see that arrival time has varied. So here you can see that we need an additional queue to demonstrate this round robin scheduling. That queue is called as ready queue, where you can easily understand how the process are waiting in the queue and how the process are picked up and given the CPU. So this is your ready queue and this is your game chart. So let's start with considering the process 1. So at 0th time the process has arrived and it is waiting in the ready queue. So P1 has arrived and it is waiting in the ready queue. So no other process has arrived, and here the problem statement which is given, we need to consider the time quantum as 4 milliseconds. So this is your time quantum, and I have picked the first process for its execution. So P1 has taken first and it is executed for 4. It starts from 0. Now you can see that P1, what is the burst time here? 5 minus 4, and remaining is 1. And meanwhile I complete this P1 and remaining all other process, that is P2 and P3 has arrived and they are waiting in the ready queue. Which process has arrived next? The P2, and after this P3 has arrived. So P1 we have taken for execution, so no need this one. So we have taken it is executed for 4 milliseconds. So once it is completed its execution, still it has to execute the remaining burst time. So what I do, I take this process and put into the ready queue, that is P1 has kept here. So whose chance is next to get the CPU? That is P2. So what I did, P2 has taken from here and give the execution, and it is executed for 4 milliseconds. The time quantum is given, but the burst time is lesser than the time quantum. So whatever the burst time is given, I execute that much. So only one time quantum which is given here, so I execute for only 1 second. It is 5 here. So now P2 has completed its execution because it has given only 1 millisecond. It is done. So fine. So the next chance it is given to P3. So P3, next waiting is P3. What is the burst time here? It is 4. So what I did, I take it from here and I execute P3. So what is the time quantum? The 4, and also burst time is 4. So I execute it completely. So now you can see P3 is also completed its execution. So the only process which is remaining here in P1 is which is waiting in the ready queue is P1. So what I did, I picked it and I execute for how many seconds? Only for 1 second. So P1, it is executed for 1 second. So no need this one, kindly ignore this. don't write this one. So the time is, so this is your Gantt chart, means the time has ended, means all the process completes its execution at 10 millisecond. So this is how we get the Gantt chart and also the ready queue. So I'm done with all the process. Now let's calculate the completion time. So completion time of P1 it is 10, P2 it is 5, and P3 it is 9, and turnaround time it is 10 minus 0, it is 10. Next 5 minus 1, it is 4, and 9 minus 2, it is 7. So average turnaround time would be 10 plus 4 plus 7 divided by 3, that is 21 divided by 3, it is 7 milliseconds. This is your average turnaround time. And what is the waiting time here? So 10 minus 5, 5. Next 4 minus 1, it is 3, and 7 minus 4, it is 3. So average waiting time would be 5 plus 3 plus 3 divided by 3, that would be 11 by 3, it is 3.66 milliseconds. So this is the solution for this problem. Let's consider another example here, where you can see 4 processes are there and different arrival time with this process, and also the time quantum which is given for this problem is 2 milliseconds. And also there is an additional term or thing that we need to identify, that is response time for these individual process. So as I said that in order to understand this round robin scheduling, we need an additional queue that is called as ready queue. So I have written this one. Along with this, we need a Gantt chart. Okay. So let's start with this problem. So as you know that whenever the process arrives, they are kept in the ready queue. So which process has arrived first? At time 0, the process P1 has arrived and it is kept in the ready queue. So no other process has arrived at the same time. So the process P1 has taken from this ready queue and it is given the CPU. So what I did, so P1 has taken here and it is given for execution, so it completes its 2 time quantum. And also you can see here it is 6, and I have to execute only 2 milliseconds, so I am done with 1. So now what is the remaining here? 4 with respect to the P1. So meanwhile P1 completes its execution. So at the time at the time 1, the process P2 has arrived, that is P2 has arrived. So after completion of this P1, it has to send to the ready queue, and also it need to check that whether at the same time any other process has arriving or not. So at the time 2, no other process has arrived. So what I did, I kept P1 here, fine, which is in the ready queue. Now what I did, I taken the P2 from the ready queue and I execute it for 2 milliseconds. So P2 is here, and remember it is completed at a 4th millisecond, and also the P3 has arrived at the same time, that is P3 has arrived at 4th millisecond. So which process has to be kept in the ready queue, either P2 or P3? So now the chance is given to the P3. Remember this one, because there is means after completion of execution P2, it has to save whatever it has executed till now, so that whenever the next time the CPU is given to this process, it has to resume where it has been stopped. So the saving, that is the context switching process, will be done here. So hence the time will be consumed for this P2. So hence it is kept after the P3 arrivals. So P2 is kept here. Fine. So how many seconds the P2 has executed? 2. Now remaining is only 1. Now the P1 has arrived. It means P1 is in the ready queue. So that is taken from here, and you need to check any other process has arrived. No, till now at the time 4 milliseconds, no other process has arrived. So the chance is given for P1. So P1 will execute for 2 milliseconds and it is 6 here. So now you can see here P1 has completed at a 6th millisecond, and meanwhile the new process has arrived, that is P4 has arrived, and I kept it at in the ready queue. So once the P1 execute, it's a 2 millisecond, I push into this ready queue. So the P1 is here now. So now which is the process is waiting in the ready queue? That is P3. So P3, what I did, I took and I given CPU for this, and I execute it for how many milliseconds? That is for 3 milliseconds, but the time quantum is given, so the remaining is 1. So 8 here. So once it is done, it is pushed back to this ready queue. So P3 is sent back. Now which process is waiting in the ready queue? P2. So take this P2 and give the chance. What is the remaining time here? For P2 it is only 1 millisecond. So I execute it and remaining is 0. So now P2 here. So it completed its execution and no need to send back because the burst time is done. Now which is waiting here? P4. What is the P4 time quantum which is burst time which is given? 5. So remaining is 3. So P4 I execute it and I send to the ready queue. P4 here. Done. Now which is waiting? P1. So P1, the time which is left is, here it is 11. Here P1, the time which is left is 2. So it is executed completely, and the time quantum is also 2. So the time is 13. So P1 is done and also P2 is done. So this is done. The next process which is waiting here in the ready queue, that is P3. So what is the burst time here? 1. So take this and you execute it for 1 millisecond, that is 14 here. So once it is done, the only process which is left in the ready queue, that is P4, that is I take this and I execute it for 2 milliseconds, so 16. What is the remaining time here? Only 1. So P4 is again, it is executed for 1 minute, that is 17 here. So this is how the ready queue and also drain chart will tell you how the executions of the process and how they have been picked from the ready queue. So now we shall see with the completion time. What is the completion time here? You can see that is P1 has completed at 13, P2 at 9, P4 at 14, P3 at 14 and P4 at 17. Now what is the turnaround time? It is 13 minus 0, 13, 9 minus 1, 8, and 14 minus 4, it is 10, and 17 minus 5, it is 12. So the value is 43 divided by 4, it is 10.75 millisecond. That is your average turnaround time. Now let's see with the waiting time. What is the waiting time formula? That you know, that turnaround time minus burst time. So 13 minus 6, 7, 8 minus 3, 5, and 10 minus 3, which is 7, and 12 minus 5, it is 7. So the value is 26 divided by 4, it is 6.5 millisecond. So this is the average waiting time. Now let's consider for the response time. As you know that when we consider the response time, means for the first time the CPU has given to that process, so that time will be considered as the response time. Now for the first time the process or the CPU is given to the process P1 at time 0, so the response time will be 0, and for P2 it is 2, and for P3 you can see here for the first time where it has given for at 6 milliseconds, so here 6, and for P4 it is given at 9 milliseconds. millisecond. So this is the problem with respect to the round robin scheduling. So I hope you have understood clearly with different types of problems. So this completes the round robin scheduling. So the next algorithm is multi-level queue scheduling. So this algorithm is mainly used or created for some of the situations like where you can classify the process into the different groups. So let's consider an example, that is you have divided the process into two divisions. One might be the foreground, where it is interactive in nature, that can be called as foreground process, and also another division is a background process, where you can take it consideration as batch process. So these two types of process will have different time or different time response time requirements. So you need to have a scheduling based upon these response time. So in this scheduling algorithm, the ready queue which has been partitioned, that is which has a separate queues, you can see this in this diagram clearly, that there you can see higher priority queues and also lower priority queues. Means the process are permanently assigned to one queue. Either it may be the system processes or it may be the interactive. Means once the process has assigned to the interactive process, so those processes are permanent for this queue itself. It cannot move to the interactive editing, or it cannot be moved to the batch process. This is very clear. So this assignment is mainly based upon some of the properties of your process. That could be the memory size or process priority or the type of the process. Again, remember, each queue that is here, again this queue has its own scheduling algorithm. So for example, you may have separate queues for foreground and background process. For foreground, queue might be scheduled by using your round robin scheduling algorithm. For background, you might use your first come first serve scheduling algorithm. So here, remember, in addition with this, you have to schedule among the queues which is commonly implemented as fixed priority preemptive scheduling. So let's see this one. That is in this algorithm, you can see the priority has been given. One is the first priority is given, that is which is having the higher priority, that is system process, then interactive process, interactive editing process, batch process, and student process. So each queue has an proper and absolute priority over the lower priority queues, which means that until unless higher priority process completes its executions, the CPU will not be given to the lower priority queues. So this is, you should remember. Assume that if a CPU is executing the process which are interactive editing process, if any other process which is having higher priority than this interactive, assume that system process has arrived in the ready queue. So whatever it is executing, the CPU is executing, it will preempt and the chance will be given to the process, that is system process. This is one thing. Second one is, there is another possibility that you can go with the time slice among the queues. That is, when each process gets a certain portion of CPU time which can be scheduled among itself or among its various process. Assume that you have given the chance, that is 80% of your CPU time is given for foreground process, and again that foreground process use the round robin scheduling among its process, and the background process may have a 20% of the CPU. That again, that queues will be using first come first serve basis. So this is all with respect to the multi-level queue scheduling. Now let's see with the last algorithm, scheduling algorithm, that is multi-level feedback queue scheduling. So we have seen in the multi-level queue scheduling algorithm where the processes are permanently assigned to a particular queue when they have entered into the system. That is, assume that you have two separate queues, that is foreground and background process. Means the process which are assigned to the foreground that cannot be moved to the background process, because the process do not change their nature of either foreground or background nature. So this entire setup will have an advantage of low scheduling overhead, but one of the limitation is that it is inflexible. So this is with respect to the multi-level queue scheduling. In order to overcome that, we have the other algorithm, that is multi-level feedback queue scheduling. So what actually it does, it allows a process to move between the queues. So the basic idea is to have a separate process according to the features of their CPU burst, or according to the characteristics of their CPU burst. So if the process uses too much of CPU time, then it will be moved to the lower priority queues. So if a process that has shorter CPU burst time, then it will be given as interactive in nature, and this will be treated as higher priority process. For example, here you can see in this diagram there are three queues are there. I can label it as it is 0, 1 and 2. So the first, whatever the process will come, that is given to the 0th queue, means it will be all the process in the 0th queue will execute first. So only when the queue 0 is empty, then the CPU will given to the process which are waiting in the queue number 1. Similarly, with respect to the queue number 2, that is until unless process completes at queue number 0 and queue number 1, the process will not be executed in process 2. So this is with respect to the how it will execute. Your CPU is executing at queue number 2. So if any other process that has arrived and it is in the queue number 1, so the CPU will be preempted and the process which are in waiting in the queue 1 will be executed first, and then if it is the queue is empty, then the queue number 2 will be given CPU. So this is how it works. So assume that a process has entered a ready queue. So once it is entered into the ready queue, it is given to this queue where it has a time quantum as 8 milliseconds. Assume if that process does not finish within this time, again that is moved to the process, that process is moved to the tail of the next queue where it has the time quantum of 16 milliseconds. Again, if it does not complete, again if that process does not complete, again it is preempted and it is put into the tail of the Q2. So the process in Q2 are based on first come first serve basis, but the process which are in the second queue will execute only when Q0 and Q1 are empty. So this is how the working of multi-level feedback queue scheduling. So this algorithm gives highest priority to the any process which is having the CPU burst of 8 milliseconds or less, which means that such process will execute quickly and get the CPU and finish its burst time and go off its next IO burst. So if the process having more than 8 but less than 24 milliseconds are served quickly, although with a lower priority than the shorter process. So this is all with respect to the multi-level feedback. So there are some parameters where we need to consider while defining the scheduler. That the first one is how many number of queues that you require, and what could be the scheduling algorithm for each and every queue, and what is the method used to determine to upgrade or when to upgrade a process to the higher priority queue, And the fourth is the method used to determine when to demote a process to a lower priority queue. And the last one is the method used to determine which queue a process will enter when that process needs services. So these are all the parameters. This is the end of the session 6. We shall meet in the next session. Thank you so much.